All right, let's get started. So we have previously talked about solids and liquids, and this week our focus is going to be on gases. All right, we started treating each of those different phases of matter separately. We kind of teach gases like to the aside because they behave a little bit differently, and there's kind of a big mathematical theory around gases that we're going to explore this week. Okay? So first of all, we talked about gases before. Let's make a container of gas. All right, and so we got a bunch of gas molecules floating around. All right, importantly, remember, gases will expand to fill the entire container. Right? So there is lots of space between neighboring gas molecules. Cool. And so my picture here, does this accurately represent the motion of these gas molecules? Are they just standing still in this flask here? No, they're constantly ping-ponging around, bouncing off the walls, all of them constantly in motion. Okay? Cool. So gases have this property to them that we're not really concerned about with solids or liquids because of the fact that they're colliding with the walls of this container. And when they collide with the walls of this container here, it imparts a force. All right, so the collision of gas molecules imparts a force on the walls of the container. All right, and this force is this measurable quantity that we call pressure. Pressure is force per unit area. All right, that is the force that these gas molecules impart on the wall of the container per unit area of that container. All right, so they're constantly kind of smacking up against the walls of whatever it is that they're in, imparting this force. All right, and there are two big things that can influence the pressure of a gas, or rather we can increase the pressure of a gas by increasing the number of collisions all right, if we take our sample of gas and we just increase the number of collisions that it has with the walls of our vessel, that's going to increase the pressure. All right, and the other thing that would increase the pressure is if we were to increase how fast those gas molecules were traveling. By speeding them up, by making them smack into the wall of that container at a higher velocity, that is going to increase the force that they're imparting on the walls of that container. Right? So these are two big factors here that are going to influence the pressure of our system. All right, gases, one of the most interesting things about them is kind of the history of this, because we're talking like real ancient science, okay? Chemistry that takes place in like the 1700s. When I kind of imagine things were a lot more like Game of Thrones looking type stuff than it is now, right? You had these certain places, these libraries filled with these books, and there were like 5 people that understood what the heck was in those books, right? So very, very early science going on here, okay? So I'm gonna put these dates down just because I think they're fun. I don't care if you remember them or not, all right? But these are a list of what we call the alternative gas laws. And they really lay out this kind of foundation, this theory of gases, and it stood the test of time, so we still use these today. All right. The first is what's called Boyle's law. And Boyle's law was credited to a 1662 publication. Okay, I'm pretty sure that that's because that's the lab that first figured out how to measure pressure. So it was like an unknown thing up until that point. All right? So Boyle's law established that the volume of a gas was proportional to the inverse of its pressure. All right, we have this fancy little symbol here. We're going to see this quite a bit today. And I'm terrible at drawing it, all right? But it's kind of like a half infinity sign or 3/4 of an infinity sign here. And this is just a math symbol that means is proportional to. So volume is proportional to 1 over the pressure. All right, another way of saying that exact thing is that saying volume equals some number times the inverse of the pressure, and I don't know what this is. All right, but the bottom line is as the volume goes up, the pressure of the gas goes down. All right? Again, let's think about this here. We said that the pressure, one of the big influences is the number of collisions. So if I take this gas and I all of a sudden put it in a much bigger container, there's much more room between those gas molecules, and it's not colliding with the walls of that container quite as often, right? So again, we see this inverse relationship here. Boyle's law, he took some data. He measured the volume of a gas and how that changed with his pressure. And he found that as the volume increased, the pressure of that gas decreased. All right, so as volume increases, pressure decreases. All right, this is about every mathematical way you can think of to represent Boyle's law right here. All right, and this is what we would call an inverse relationship, or inversely proportional. All right, so Boyle, with his very crude pressure measuring device, found that there was an inverse relationship between the pressure of a gas and its volume. So as the container that you're keeping your gas in gets bigger and bigger and bigger, it's colliding with the walls of that vessel less and less, so the pressure is going down. All right, next up was Charles's law. All right, Charles's law was credited to an 1787 publication. So again, not terribly recent. Charles's law found that the relationship between volume and temperature was that volume was proportional to temperature. Not inversely proportional, but what's called directly proportional. Again, I really suck at drawing that little symbol. All right, so this is what we would call a directly proportional relationship. Where if we increase the temperature, that leads to an increase in volume. All right? So if you were to take, for example, a balloon and blow it up and were to put it in an oven, I mean, assuming it made it in there okay, you would see that that balloon gets bigger. It expands in volume. Or probably an easier thing to do would be to take that balloon and put it in the freezer. And what you would find is that the volume of that balloon would decrease. It would shrink, right? Because these two are directly proportional to one another. The volume of a gas is directly proportional to its temperature. If one increases, the other one increases. Or likewise, if one decreases, the other one decreases. All right, so again, Charles made a little plot. Where he increased the temperature and measured the volume of a gas. And he saw that as that temperature increased, so did its volume. Okay, so again, directly proportional. And then this other guy came along, this other French dude, was literally named Gay-Lussac. All right, and he basically took this data and started doing something similar, but he was like, all right, I'm going to decrease the amount of gas that I start with. And he was like, this all seems to extrapolate back to the exact same temperature. If I fit a line to all of these data points, let's see how well I did, not too bad. All right, they all extrapolate to the exact same temperature, which is negative 273.15 degrees Celsius. All right, which is what? 0 degrees Kelvin, or what we call absolute zero. So on this graph here, he found that all of these gases, if he could, which he could have never done back at that point in time, if he could have decreased their temperature all the way down to negative 273.15 degrees Celsius, they would have zero volume, okay? This is kind of birthed this very important temperature scale of Kelvin. To be honest, he didn't get quite to the negative 273 number, but I think he got negative 266, pretty good for like the 1700s, all right? Regardless, this introduces this idea of absolute zero, or our Kelvin temperature scale, which is why the Kelvin temperature scale is important here. So first of all, let's just talk about Kelvin. I guess it was really Lord Kelvin that probably introduced it, huh? But anyway, this guy was onto something. Cool, so first of all, our Kelvin temperature scale is that degrees Celsius temperature plus 273.15. Now, importantly, that 273.15 is considered exact, so it will never limit your sig figs. All right, so what that means is you imagine it has just an infinite amount of zeros at the end. It's not what's going to limit where you round to. You're going to need to round to the decimal place that you have in degrees Celsius. We'll do some practice here. All right, but importantly, why the Kelvin temperature scale is considered to be like the fundamental temperature scale is because of this concept of absolute zero. Okay. Absolute zero is 0 degrees Kelvin, and at absolute zero we say there is no motion at the atomic level. Up until now, we've been doing a lot of things in degrees Celsius, and that's because sometimes it doesn't matter. Truthfully, especially if you're talking about delta T, it doesn't matter whether you're in Kelvin or degrees Celsius. But here, when we're talking about gases, we absolutely have to be in Kelvin, all right? So anytime we're talking about gases and we're doing any math with gases and our temperature is given to us in Celsius, the first thing we're going to do is convert it to Kelvin. It has to be in Kelvin for these theories to work, all right? And again, it has everything to do with this point here, absolute zero. Cool. So last one that comes along here is Avogadro. All right. This goes back to an 1811 publication who I'm pretty sure wasn't even by Avogadro, but the guy kind of like gave him a one-up for it and named it after him. Avogadro's law states that the volume of a gas is directly proportional to the number of moles in that gas. All right, and we're going to use this variable n in this chapter here for number of moles, lowercase n specifically. All right, now, Avogadro's real sort of claim to fame is the idea of like being able to count all these little teeny tiny particles, right? We've sort of already introduced moles, so it's not quite as groundbreaking of an idea to us. The idea that if I take a balloon and I put, let's say, 1 mole of gas in it, it's going to be bigger if I put 2 moles of gas in it. Hopefully that all checks out based on what we've discussed up until now. But of course, at the time, this was like this ridiculous idea that you can count all these little invisible things that are down there in this gas, right? So anyways, and this is, again, what we would call a directly proportional relationship. Meaning if we increase one, we increase the other. Cool. So all these observations are sort of combined together. All right. Boyle's law was that volume is inversely related to pressure. Charles's law is that it's directly proportional to temperature. And then whoever I'm missing, Avogadro's law is that it's directly proportional to number of moles. All right, so all this implies that our volume is equal to n times T over P times some constant that we don't know, and we call this, now that we do know, the ideal gas constant. And this is this proportionality constant. This is kind of a weird way of representing the ideal gas law. All right, so let's kind of put it in its more normal format here. What we call our ideal gas law. Does anybody remember it? PV equals nRT. Start chanting it to yourself now. All right, so this is this equation that relates these 4 different variables that we've been talking about up until this point. We have the pressure of a gas. We have the volume of that gas. We have n, the number of moles of that gas. We have temperature. And what am I going to make note about my temperature here? What does it have to be in units wise? In Kelvin. Has to be in Kelvin, or your ideal gas law just quite simply doesn't work. All right, and then we got this 5th one here, which again we call the ideal gas constant. Cool, so hopefully this is familiar, and if not, it's really pretty straightforward to use here. As far as the algebra goes, it's just multiplication and division. All right, we got these 3 variables and then this constant here. All right, so the bottom line is if I give you 3 out of the 4 variables, you should be able to solve for what's missing. Right, I give you pressure, volume, number of moles, you always got your ideal gas constant. You can rearrange this equation and solve for T, solve for what's missing, all right? We'll obviously do some practice here in a second, but let's talk about this ideal gas constant. Where do we think we're going to find our ideal gas constant? On the constants page. Cool. So if we go to the very top corner, kind of above Avogadro's number here, we have this ideal gas constant value. All right, and we got 3 of them here. So what gives? You just told me it was a constant, and now there's 3 different values. All right, let's look closely here at our units. Our first one is they all have these mixed ugly units here. All right, and that's because they're going to unify the different units of pressure, volume, temperature, and number in moles. So we have liters, ATM, moles, capital K for Kelvin. And then in the other one, we have liters, torr, moles, and Kelvin. Okay? So what's the difference here is the ATM and the torr. These are different units of pressure. Okay? You probably had to do a unit conversion in pressure just while I was making you do unit conversions, but we hadn't actually talked about pressure. So we have all these different units that we use for pressure. There are 2 of them that are the most popular in the chemistry lab, ATM and torr. All right, torr is kind of, I think, historically important because it's the same thing as millimeters mercury, which is how they measured pressure for a very, very long time. ATM, I feel like, is now becoming more popular because it's very intuitive. It is the pressure at atmospheric level, or it is the atmospheric pressure of 1 at sea level. Right? So it kind of raises or goes up compared to what our pressure is here in this room. So anyways, ATM, torr, both of these you'll see here. All right? But importantly, given one, we can always convert between the other. We also have our Kelvin conversion factor down here, just FYI. It's got the little stars because that 273.15 is exact. Cool. So anyways, we got these different units for pressure. The other one looks a little weird. It's mole, Kelvin, and then it's joules. That seems kind of out of place unless you remember what we were talking about with work and the fact that you can actually convert from a liter ATM to joules. All right, so again, just another conversion factor. All right, the bottom line is which one you're going to use is going to depend on the units in your problem. Okay? All right, so let's just do an example using the ideal gas law here. All right, 25.3 liters of an ideal gas. Are kept at, let's say, room temperature, 23.5 degrees Celsius. And 1.3 ATM. How many moles of gas? Are in our sample? All right, so you're going to start out with that PV equals nRT equation. Importantly, what is it that we're being asked to solve for in this problem? Moles. So that means we're trying to solve this equation for N. You know, some people like to plug in numbers beforehand and then rearrange. I think it's a little bit simpler to rearrange symbolically, but you know, you do you know your preference here. Okay, but importantly, let's think about what that value for the ideal gas constant should be here. All right, we have our units of liters for our volume. And we have units of degrees Celsius, which we're going to have to convert to Kelvin for our temperature, because it has to be in Kelvin. Our gas is given at a pressure in ATM, and we're going to be answering number of moles in moles, of course. So which one are we going to use? That very first value. at 0.082058 liters ATM mole Kelvin, per mole Kelvin. Cool. All right, I'll grab this and take it back to the other page. I want y'all to see if you can't answer this ideal gas law problem on your own. All right, so let's go through this. So the first thing I need to do is to convert my temperature from degrees Celsius into Kelvin here. And I'm going to take that and add that 273.15. But again, this is exact, so it's not going to limit my sig figs. Remember, when you do addition, it's all about your position of your smallest sig figs. So that means my when I add my 273.15 and get my temperature in Kelvin, my temperature in Kelvin has these 4 significant figures. Cool, so I'm just going to keep my position marked with the little bar over here. All right, what I did was I took the ideal gas law and I rearranged it by dividing both sides by RT. That canceled it out over here, leaving me with my number of moles all by itself. So that's how I got as my equation, number of moles equals PV over RT. And I plugged in my variables here. All right, I'm going to punch it into my calculator somewhere. I get 1.37707. All right, and what are my units? Oh, no. Yeah. Hold on. Is that not what? I feel like I got some weird looks here. Okay, hold up. Let me just. I feel like I've been worse lately. End of the semester. 1.38?
5, 4.
Yeah, okay. I must have swapped something. I did do a 23.5 and a 25.3 in the problem, not thinking about it, so that was maybe where things went awry here. Okay, my bad. 1.38543. Okay, and what about my units here? So they should be in moles because I'm solving for n, but let me just sort of show here the long way that that is what our units of R are doing for us. They're these big, ugly mixed units, but they got everything in there. So ATM cancels out, liter cancels out, Kelvin cancels out, and I'm left with units of moles. All right, then the last thing that we got to do here is sig figs. We have 4, 3, 2, 3, 4, 5. This ideal gas constant is not exact, but it does have a bunch, so hopefully it doesn't limit us. All right, and so my final answer, I'm going to have to round to 3 sig figs, or 1.39 moles. Cool? So our ideal gas law here, it tells us that the pressure times the volume equals number of moles times that ideal gas constant times temperature. All right, we got one constant value here that we always know. And then if I give you 3 out of the 4 variables here, you can always solve for what's missing, right? Just from an algebra standpoint. Cool, so the other thing that we can do with the ideal gas law is we can actually derive not only the alternative gas laws that we discussed, but a bunch of other ones as well. All right, and so these are kind of like, I don't really know what to call them other than like before and after kind of problems. Meaning that you're given initial conditions about some of your variables in the ideal gas law. And you're asked for a new value after a change is made. All right, so let me put down, and I feel like if we just kind of learn by example here, it might be more efficient. Okay, so we're going to add 1.0 moles of helium to a balloon. And its volume is 20 liters. Now we're going to take this same balloon and we're going to add more helium so that we have a total of 2 moles. And we want to know what is the volume. All right, so I told you about the conditions of this balloon before. There's 1 mole and it's got a size, it's 20 liters big, right? And then I'm going to make a change. I'm going to increase the number of moles of helium in that balloon, and I want to know what happens to that volume. Okay? So first of all, what do we think? Is it going to get bigger or smaller? Bigger. Okay, cool. And in fact, since I'm doubling my number of moles, we're going to see that we double the size of that balloon. All right? And this is just Avogadro's law, but importantly, we're going to sort of derive that using our ideal gas law here. All right, so we're going to start out with our PV equals nRT. All right, and importantly in this problem, we're only changing 2 things here, right? So there are certain things in this ideal gas law that we are varying. Those are our variables. And then we have other things that are remaining constant. They are not changing. That's what we got to do here. We got to figure out which one of these 5 things is changing, which ones are remaining constant. So one of them is always remaining constant. All right, so which one is that one that I can color green real quick? R. R is the ideal gas constant. It is a constant. Its value is definitely not going to change. Okay? If we read our problem carefully, what are we changing in this problem? What am I increasing from 1 to 2 moles? Oh, I guess I just gave it away. Yeah, helium from 1 to 2 moles. So the number of moles is changing. All right, and when that number of moles is changing, I'm expecting to see a change in the number, or rather in my volume. All right, so my pressure is not changing. My temperature is not changing. All right, without any other information, we're just going to assume that these things are held constant, which it would be for a balloon that's sitting in a room like this. All right, and now we're going to, so first let's just make note. We're deriving this business here. So how are we doing this? Step 1, we're going to identify our variables and constants in the ideal gas law. Okay, and now what we're going to do is we're going to use some algebra. Oh man, algebraically, I don't know. Algebraic-ish, rearrange. So all of our variables are on one side and our constants on the other. There we go. Cool. All right, so I want everybody to take a second. Given our ideal gas law, given that we've indicated that volume and number of moles are variables, but the rest of them are being held constant, rearrange this equation so that all the variables are on one side and all the constants are on the other. right, so in order to move my pressure away from my volume, I'm going to divide both sides by pressure. And then I need to get N on the other side, so I'm going to divide both sides by N. So that cancels it out over here, cancels pressure out on the left and N out on the right. And so what I'm left with is volume divided by number of moles equals RT over P. Cool. All right, so in my problem, it's telling me here that this ratio, volume divided by number of moles, is equal to some constant value. Now the volume's not constant, and the number of moles aren't constant, but their ratio is. If I take the volume divided by the number of moles, I'm going to get the same number no matter what my conditions are, because everything else is being held constant. So that means that before this change was made, my volume divided by number of moles is equal to some constant value. We're going to put a 1 here to indicate we're talking about before. And that has to be the same as that same constant value, my volume divided by my number of moles after that change was made. And we're going to use this little 2 here to indicate that we're talking about after the change was made. So since volume divided by number of moles has to be equal to some constant value, that means my volume over moles beforehand has to be equal to volume over number of moles after. And this is just a kind of fancy restating of Avogadro's law. But again, we sort of just started with our ideal gas law and we derived it ourselves. And so we can derive even more alternative gas laws, even that aren't as famous and have names associated with very long dead scientists. All right, so given this equation here, I want everybody to take a second and see if they can't solve our problem. All right, I'll move this text of this problem down. Cool. All right, so to be clear, my V1 in this equation and my N1 are the initial conditions that I'm being told about this gas. All right, so I have 1 mole of helium, that's my N1, at 20 liters, that's my V1. I'm then told that we put 2 moles of air in there, so that's my N2. So then I'm solving this equation here for V2. And I'm just going to rearrange using algebra, multiply by N2 on both sides. I get V2 equals V1 over N1 times N2. And I'm going to plug in my values for my problem. My V1 was that 20 liters. My N1 was that 1 mole. And I'm going to multiply by that 2.0 moles. And so indeed, as we sort of had said intuitively, we double the number of moles, we double the volume to 40. All right, and actually that's not correct. So we got to worry about sig figs here. So first of all, units wise, importantly because I'm dividing and multiplying by moles, that cancels out and leaves me with units of liters, so I was way off anyway. All right. We're getting close to the end here. It's tough towards the end. All right. Importantly, sig figs. We have 3 on the 20.0 and 2 for our number of moles. So I'm going to leave this decimal place here to indicate that I have 2 sig figs in that volume. Cool. All right. So before we move on, I want you all to practice. The plugging in step is fine, but this step of identifying variables and constants and rearranging is kind of weird. All right. So what I want you to do is find me the relationship when, let's do pressure and moles are varied and everything else is constant. All right, take that ideal gas law and play that exact same game that we did before for volume and number of moles, but now for pressure and number of moles. All right, so I'm going to use some algebra to rearrange this equation here. Got everything that I identified as variable on one side and everything that's constant on the other side here. Right, so now even if I vary my pressure and my number of moles, as long as everything else is held constant, pressure divided by number of moles will be constant as well. So if we put that into our before and after relationship, that would be the same thing as saying P1 divided by N1 equals P2 divided by N2. Okay? All right, and that should sort of check out in terms of what we were saying about pressure, how we can increase pressure by increasing the number of collisions. Well, one way to increase the number of collisions is by adding more gas molecules, right? There'll just be that many more collisions per unit time. So when we increase our number of moles, we increase our pressure, and we could use this relationship here to track exactly how much of that is true quantitatively, right? We could then plug in the numbers and show that mathematically. And we got that by taking our ideal gas law and identifying what was variable and what was constant, and rearranging it so that all of our variables were on one side and all of our constants are on the other side. Cool. All right, there is one more very old scientist whose results we're going to talk about here, and this is Dalton's law of partial pressures. Okay. Cool. All right. So what we're going to do is we got 3 canisters here of gas. All right, one of them we're going to fill with argon. And it is totally arbitrary what gas I'm picking. But importantly, in the other one, we're going to fill it with a different gas. We're going to fill this one with neon. And then we're going to take these 2 containers and we're going to combine them together into one that's the exact same size, but now contains a mixture of these 2 gases. Okay, so now we have a mixture. And this is what we're going to use this concept of partial pressures to talk about, is mixtures of gases. All right? So the question here is I want to know what the pressure is in this mixture, what we're going to call the total pressure here of these 2 gases combined. Okay? Well, for argon, I could have taken my PV equals nRT and rearranged it. So if I know the number of moles of argon that I have in this sample, times R times T over the volume of this canister, well, that would give me the pressure of argon over here in this canister. Cool, thinking about it before I combined them together here. And if I wanted to know the pressure in this canister of my neon, I would just need to know the number of moles of neon. I got my ideal gas constant I always know, times the temperature of my gas divided by the volume. Okay, so what we learned how to do for separate gases, we can figure out their pressures using the ideal gas law. So then what if we have a mixture of gases here? All right, it turns out that the total pressure here is just going to be equal to what we call the partial pressures of each of these gases. So in this case here, my total pressure would just be equal to the pressure of argon plus neon if I know how much argon I have, and I know how much neon I have, and I know the temperature of this canister and its volume, I can figure out the total pressure of that system. It's just the simple sum of the 2. All right, and we'll talk about a little bit more about like what it means to be an ideal gas next class. But the bottom line is, notice that nowhere in this discussion of gases have we factored in what gas we're talking about. Right? The ideal gas treats all gases the exact same. It kind of imagines them as just little marbles bouncing around inside that container. So it doesn't matter if I have argon or neon, I'm going to treat them the exact same using my ideal gas law here. Okay? So this is Dalton's first formula here. So we're going to call this Dalton 1. All right, and that is that the total pressure in a mixture is equal to the sum of the partial pressures of the gases in that mixture. We can summarize that mathematically using this formula here. All right, but again, stated out, in sentences here, this says that the total pressure of a mixture is the sum of the partial pressures of gases in that mixture. Okay? Cool. So now we're going to take Dalton 1 here, and we're going to derive another important expression. We'll use our example. We said that the pressure total was equal to the partial pressure of argon plus the partial pressure of neon. All right, and then we said, well, we know our equation here for those partial pressures. That's just the number of moles of argon times R times T over V plus the number of moles of neon times RT over V. Okay, now let's think about it. In this canister here, are both of the gases in that same volume canister? Yes, and if they're in the same canister, they also have to be at the same temperature, right? So there can't be any volume or temperature difference between these. R is also going to be the same because it's always the same, right? So I can combine this together. So number of moles of argon plus number of moles of neon times RT over V equals the total pressure. All right. And so the total number of moles in this mixture here is equal to the number of moles of one gas plus the number of moles of the other. So my total pressure is equal to N total times RT over V. Okay, and so now it's even more fun than that. Don't worry about it. All right, so now what we're going to do is we're going to take our partial pressure of, so for example, argon, and we're going to divide it by the total pressure. So this thing here, divided by now our newly defined here total pressure. I want you to take a minute and to simplify this equation as much as you can. All right, when we divide a fraction by a fraction, what do we say? We multiply by its inverse. So I'm going to take my first fraction and I'm going to multiply it by the inverse of my second fraction. And what do I get to cancel out here? R, T, volume. All right, so what I'm left with is my partial pressure of argon over the total pressure of that mixture is the same as the number of moles of argon divided by the total number of moles. And that is a quantity that's already sort of had existed before, and this is going to lead us to what we call Dalton 2, which is really just derived from Dalton 1, but it looks a little bit different, which tells us that the mole fraction of a gas okay, we use this fancy little uppercase X thing for this mole fraction is equal to the number of moles of that gas divided by the total number of moles in that mixture, which we also just established was equal to the partial pressure of that gas divided by the total pressure. All right, so if you have a mixture, you can always define a mole fraction, where you take the number of moles of whatever you're interested in divided by the total number of moles in that mixture. That's this new quantity we use, or we call mole fractions. All right, and it turns out that for gases, that mole fraction is also equal to the partial pressure of that gas divided by the total pressure. Cool. All right, so let's use Dalton's law here. Okay. All right, so let's actually put them both next to each other. We got Dalton 2 and Dalton 1. So at 10,000 feet, a sample of gas has a partial pressure of nitrogen equal to 0.69 atm and a partial pressure of oxygen equal to 0.20 atm. All right, and so using Dalton's laws here, I want you to tell me first, what is the total pressure? And then secondly, what is the mole fraction of nitrogen? All right, so for the first one, I'm going to need to use that Dalton 1, because that tells me that the total pressure is equal to those partial pressures, the sum of those partial pressures of my two gases, nitrogen and oxygen. All right, this is an addition problem, so I'm going to be good here. I'm going to take my 0.69 ATM. I'm going to add my 0.20 ATM. This will give me a total pressure of 0.89 ATM. All right, and my sig fig is in that hundredths place. Okay, so this is the total pressure on top of this mountain here, 0.89 ATM. Cool, so now in order to get my mole fraction, I'm going to need my other expression. All right, and let me be clear, because this is something that always kind of trips people up with this formula. Okay, and that is quite simply that it's got too many frickin' equal signs. All right, everybody tries to use it as is and plug stuff in, and then you're always missing too many things to solve for. Okay, this is not summarizing just one equation. This is this nice compact form that's actually showing you three different relationships here that are all equal to one another. This is telling me that my mole fraction is equal to the number of moles of my gas divided by the total number of moles, without this here at all. It's also true that my ratio of my number of moles of gas to the total is equal to the ratio of the partial pressure to the gas to the total pressure. All right, or likewise, that my mole fraction is equal to the ratio of the partial pressure divided by the total pressure. So you only ever use two out of these three terms at one time. You don't use all three of them run together. We just use this as a nice, neat way of displaying these three relationships, right? But this is really this relationship here, and this one here, mole fraction over the pressures. Boom. All three of these are summarized into that one line. But you'll only ever use one out of the three of these at a time, right? It's just a compact way of showing those different relationships because they're all equal to one another. So in this case here, I'm going to need which one? A, B, or C? C. I need my partial pressure divided by my total pressure is going to give me that mole fraction. Cool. All right. So all right, I'm going to take the partial pressure of that nitrogen gas, which is that 0.69 ATM, divided by the total pressure of that gas, which was the 0.89 ATM that we just calculated. Punch that into my calculator. I get 0.77528. Okay, what are my units here? Careful, it's not ATM because I got ATM on top and on bottom, so what's going to happen to those two ATMs? They're going to cancel each other out. So this is an example of a unitless value here. Mole fractions don't have any units associated with them. These are not super duper common, but we do see them in chemistry. There are a few values that don't have units. Mole fractions would be one of them. They do still have sig figs though. All right, so when we do our sig figs, we got 2 in the numerator, 2 in the denominator. So my mole fraction of nitrogen gas is that 0.78. All right, you will see this also gets very similarly related. You will hear that that air is 78% nitrogen, right? That corresponds to, in fraction form, that mole fraction, right? Remember, percentages, for whatever reason, we like looking at percentages, but you kind of arbitrarily multiply by 100. So if we turn that back into fraction form, that's what they mean by air is 78% nitrogen, that the mole fraction of nitrogen in air is 0.78. Cool. All right.